All right, so let's start. So there is a reason why it will become clear increasingly in the coming weeks why perhaps I am trying to provide these alternate motivations to study this subject. So the bottom line is that it's very easy to get lost in the formalism. Like we are caring about all the sequences, limits of sequences, and worrying about convergence and how fast things are converging and so on. So it's very easy to get bogged down, or not bogged down, but rather get overwhelmed, or let's say a bit distracted by the kind of mathematical machinery or understanding that we need. Of course, that's necessary, but at the end of the day, we are trying to model some situations and trying to find solutions to those problems. So this is something that goes back to first century AD. Just a second, let me hold on if it's recording or not. Okay, yeah, good to go. All right. This is first century AD, roughly, and this is from a book called On Mirrors.
Deep, are you sharing your whiteboard?
Okay. Sorry, extremely sorry. I thought I was sharing. Just a second. Can you see my board?
Yeah, it started. Yeah, now I can see.
Okay. Yeah. Sorry. So yeah, welcome to week 3. So I just wanted to start with a somewhat of a story-like problem. So this goes back to. So let me just remove this one, or I'll come back to the name later. So there's this first century AD book. It's by Heron, and the problem is, well, you would have seen this problem, and you all probably also know how to solve this, but let's just go through it anyway. So A and B are 2 points on the same side of a line L. Find point D on the line L such that AD plus DB is minimum. So pictorially, if I have A, B, and I have D, and so I'm given, I mean basically I have to find a point D on this line L such that this AD plus BD is minimum. So how would you go about this? Any thoughts?
Yeah, I think it should be geometrically possible, right? By
Yeah,
completing
just
the triangle.
geometric solution. Yeah, so think that you don't have calculus here because you are in first century AD, so you don't have that kind of machinery available to us. So some argument which is relying on simpler principles. No calculus needed.
So can I assume that when angle DADB is 90 degrees, the shortest something along?
No, you can't assume that. So you'll have to prove that. For example, I mean that won't be the case, by the way. Will that be the case? I don't think so.
Uh, yeah,
Okay,
because
something simpler than that, perhaps. So how so you what are we given here? So let's see. So what are we given here? We are given this height and this height, and we have to find a point on this. So all this is all we are given. We are given 2 points on the same line, and we have to find the point here. So let's say this is the region of interest, right? So how would you want to put this point? So one criterion you said right angle. So is any reason that you feel this could be this is something plausible, like the rationale behind saying it should be a right angle? So okay, right angle, sorry, let me rewrite this. So okay, attempt 1 is angle ADB, right? You're saying ADB is
Yeah.
90 degrees. Okay. If first of all, if it is correct, and if so, why do you feel that this would be the right way to think about this?
No, I was just thinking that we have if I complete a triangle and one side of a triangle is fixed, so if we can somehow compare the length of the two sides to something else.
Okay.
Uh,
Okay. So you are, yeah, you are onto something for sure. So let me present this. It's a bit intentional. I wanted to put this answer is deceptively. It's what you would expect in hindsight. So let me just think of it like a mirror. Let this be a mirror.
okay,
Okay.
okay. You extend the D onto the opposite side, right?
Yeah.
With the same distance.
Yeah.
And then extend.
So now
Yeah,
you just
yeah,
draw a straight line, right?
yeah,
Because straight line is the shortest distance,
yeah.
right? So what you would do? You will just, this is your point, so D prime. That is your point of interest, right? Is so AD prime plus D prime B prime equal to, okay, someone trying to join. Oh. So this let me, can I shift this? No. Let me write this properly. So let's still write it, even though it's pictorially it's clear now. Let's still write it why it should be true. So let's say A D prime plus D prime B prime equal to A D prime plus uh, D prime B. Is this correct? From here to here, these two things are equal, right? By definition, because we just took a mirror image. So this and this is basically the same. Okay. All right. So what else can we write here? So this is greater than AB, right? Triangle inequality. Does that make sense?
Yes, yes, yes.
So what we have proved is, what have we proven? Okay, is it not clear? Should I explain it again? Okay, I think I'm hoping that this is clear, because to test this, we what we'll do is we'll just write a few more similar questions and just see if we can apply this kind of reasoning. So yeah, just for completeness, so this book, oh, sorry, so this book by Heron is called On Mirrors. Okay, it's a first century AD work. We don't have any original documents from this book. We just have references about this person thinking about these questions, and this was in the context of, at the time, it was about light. How does light travel? And Heron provided an answer, which is light travels along shortest path. Okay, so we'll just quickly go through some similar questions and then we will go to the assignments. All right. I think what I'm going to do next week, just as a teaser, we'll solve something similar. So we'll see light travels along path taking minimum time. What if we solve that optimization problem? What we will get. So again, to reiterate, the whole reason why I want to do this is because I want to keep emphasizing this point that we are trying to model these different situations, and that's an important part. You may see in the course we do care about a lot about, things are well defined, and we are making sure that okay, this is convergence or divergence and speed of convergence and whatnot. But the modeling is another important aspect, and I hope to at least convey you the importance and the exciting aspects of also trying to model problems, whether it's a bit historical in nature or whether they are contemporary. Okay, so all right, so if we got this idea about finding the shortest path between 2 points on the same side of the line, okay, so then what about this kind of a situation? So you are given a point in the interior of a given angle. Okay, so what we have to do is find points A and B on the sides of this angle. Such that the perimeter of the triangle ABC is minimum. So what I mean is, pictorially, if I have this angle given, I have a point C in the interior of the angle. What I need to find is, I need to find some point A, some point B, such that the triangle that is formed here, that has a minimum perimeter. So what I'm saying is, minimize AC plus BC plus AB. So how would you go about this? Any thoughts? Again, no calculus arguments, just some geometric arguments.
The
Okay,
point C is
yeah.
fixed, right?
Yeah, C is fixed. C is given. So what you can change is A and B. So okay, maybe let me. So actually, that's exactly what I was going to ask. Good that you asked that. So can you help me write down what is the optimization problem? Although a part of it I've written here, but can you help me write down the exact optimization problem? So let me call this line L1, and this line is L2. So what I'm saying is, this is line L1. Imagine there's rather a ray here, and there's another ray here, call it L2. So now that you know this, can you help me write down the optimization problem, what we are trying to solve here?
So it will be the same thing, right? Minimize AC plus this thing, subject to some conditions.
Yeah,
BC
so
plus
for okay,
AB.
before the condition, minimize what with respect to what? What are the variables?
Minimize. Okay, minimize the.
So see, this is the objective, right? This is the objective function.
Yeah.
What are the variables? So if this is f of x, what is x here? Is there one variable, two variable, three variable, four variable? How
There
many
are two.
variables?
There should be two variables, right? One variable on the segment AO means if you
So
consider O as the
basically there are
origin.
two variables a and b, right? I mean, like, we will be a bit informal here.
Yes.
We just say indicate the point here. It's all right. A and b are some points in this Euclidean space. Okay. So you said something very important. There is some constraint. What is that?
That point A should lie on the line AO and B also on the line BO.
Right. So what you're saying is this. Yeah.
Yeah.
So I mean, this is exactly what we have been starting to study, right? It's not so easy to solve this problem because this constant in general could be very complicated. The surfaces that could be very complicated. So, just want to allude to that. We will be coming to this quite soon. But is it clear to everyone how do we formulate this problem? So you see that even a simple problem like here, you could now solve it using the tools that you have seen in week 3, right? As long as it's an equality constraint, you have the machinery to solve this, right? But I'm saying let's not do that. Let's just try to argue from first principles. Yeah. Sorry, my screen is paused. Just give me a moment. I mean, the screen has a break timer. Just give me a moment. Yeah. I hope you're still able to see my screen.
Yeah, it's visible.
Yeah, okay. So how would you go about solving this?
And maybe Deep, I have a suggestions.
Yes.
These problems need a little bit of thinking. If we can give like this problem on first class and tell us to think about it and come back again to the following class about the ideas, I think that would be a little bit more this thing.
Yeah, I mean, so the thing is,
Open.
yeah, there's a lot to cover, so I'm just trying out a few
Yeah,
things.
because just telling some answer randomly doesn't look good. That's why.
No, don't worry about that. I mean, that's exactly the point, right? Just thinking out loud. That's why it's perfectly fine to not get it the first time. It's not that it's supposed to be easy or hard. It's just meant to make you think about formulating the problems. For example, this is a good step. Now that you've pointed this out, so yeah, in principle, we could solve it using this, which is what you have seen in your week 3 lectures 5 and 6. But I'm saying let's not do that. We'll come to that. But I'm saying in at least in situations like this, you could do something straight, something. So let me give you a hint. We have to use this idea. There's a reason why I started with this problem. So it's it was implicit that we have to use some property, some ideas like this. So what can we do? The first thing that we can do. Can we do something? Can we use this? So how about just finding A first? Forget about B. How would you find A if you are given C? Just intuitively, what do you think? Where should A be to have a minimum distance between A and C?
Yeah, it should be a perpendicular to.
Yeah, exactly.
Means AC should be perpendicular.
Exactly. right? So what have we done? We have minimized this, right? Yeah.
Yeah.
Okay, so now what? Now how do we use this? So now I have 2 points on the same side of the line. What can I do to minimize this plus this? So again, going back to the same example, you have line, 2 points. How do you minimize the distance? You just take the mirror image of this, right? So you have this point, you have this point, this is the line. You have already minimized this. Now you want to minimize this plus this, right? Why? Because you are minimizing the perimeter. Yeah. So you just take a mirror image of this here. So you have a point somewhere here, and you just draw a line, straight line. So you have A, B, C. So exactly like what we did before. So you take C prime as the mirror image, and this implies find B on the straight line AC prime. Okay, so this is how you will get minimum of AC plus. Okay, I don't need to write this. So I have found my A and B. I'll just leave you with 2 more questions. You can try it out, and if you are finding any difficulties, let me know. Okay. There's 2 more questions along similar lines. I'm already giving the hint. So what you have to do is, now you have, instead of 1 point, you have 2 points in the interior. So find AB such that you are given C, you are given D. You have to find A, as usual. You have to find A on this side and B on this side, such that the sum of the following sides is minimum. So sum of AC plus AB plus BD. So what you have to do is, you have to find points here and here such that this distance is minimized. So previously C was equal to D. I just changed that. I made C not equal to D, and we still care about minimizing the sum of these 3 sides. So again, the hint is you have to use this mirror image concept to do this. Let me know if you are finding it difficult. One more question, again along similar lines. Find D such that minimize AD plus DB plus DC. Now what do I mean by that here? So what I'm given is, I'm given A, I'm given B, I'm given C. I'm given 3 points. I want to find a point D on this line. D on the line L. So this is my line L. Such that this distance between point on this line with each of these A, B, C. Can you tell me why this kind of problem, by the way, would make sense apart from just the curiosity, mathematical curiosity? Specifically this problem. Can you think of an example, like a real life example, why solving this kind of a problem might become relevant? Please don't worry about thinking that it could sound wrong. Just think out loud. We are trying to come up with situations where this kind of a problem formulation could help us. Anything from your daily life that you can think of? Any thoughts? I won't be able to read the messages, so can you please speak up? Yeah, you said transportation, so can you just maybe briefly elaborate on that?
Hello, is I'm
Yeah,
audible? Okay, suppose there are city A, B, C. So we have to send a parcel from A to B and B to C. And there is a center city D. So it will be get easy to send a parcel from A to D. Means D will behave as a center dock where the all the parcel will come and then dispatch to the their particular
right.
final destination.
Right, yeah, 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 great, yeah. Yeah, so in general, if you know, in supply chains, this is a very common and routine problem that, a routinely encountered problem that, you have these, let's say, locations A, B, C where you want to supply different things. It could be food, it could be water, it could be any commodity. And point is, you can't set up your units to sorry, ABC are the demands, not the supplies. So you can't set up units near ABC separately to satisfy this demand with your supply. You just have to find one supply unit. And how would you go about doing that? So this is like a very very simplistic way of a very cartoon toy version of the same problem. So in general, uh, because you have started seeing constraints, you could have, very generally speaking, so this, I'm just writing a generalization of this cost. What you can have is, so what you have to do is you have to minimize x1, and you will have constraints for each city. Okay, so what I mean by that is, let's say there are m places where you need to supply something, some resource. Okay, and you are not sure how to split, how to supply what amount, I mean what amount to supply to each of these m places. What you know is, roughly speaking, what is the cost associated with supplying a single unit of resource to that place I, that ith place. That's what you have. And this is like a very simple case where I'm just adding up all the costs, which is understandable, right? If I have costs of 300 rupees per kilogram, I just want to determine how many kilograms to send, of supplies to send to, let's say, place I. And this will be subject to some constraints, like for example, I can't use so much, I can't use fuel more than this, or I cannot delay my supply time to, let's say, more than x number of days, and things like that. Okay, so just try this out in this very very simplistic setting and see if you are able to solve it. So that's it for the stories. Let's move to the questions now. Before I move on to the week 2 questions, because we couldn't discuss it last time, any questions about Taylor's theorem, whatever has been covered in the class?
Deep.
Yes.
So what the instructor was telling a version means, he was, when he was proving Taylor's theorem,
Yes.
he was phrasing it in this way, that why open ball around one point, if we have an open ball inside a set, why that suffices, means from if we start from any direction, that can be scaled down to be contained in that ball, along those lines. So I was just wondering if in certain special type of sets those things can fail, means all the points cannot be reachable from a local point.
When you say all the points, what do you mean?
Means all the points, the region where I'm optimizing in the feasible region. He
Right.
was suggesting that if there is an open ball, any region that can be reached from a particular point can be scaled down to lie within that ball, and so that we can reason accordingly. So are there cases, some sets where this thing, that reachability argument can fail, means some regions, it's obvious that if the set is disconnected, that it may fail. But are there any other cases that this argument can fail?
Yeah, so I think Euclidean spaces, I mean, I have to think a bit about. So, okay, like if I understand correctly, what you're asking is, in general, if I have an open ball, let's say just the regular Euclidean space, I have an open ball. If I take any point inside this ball, and I can look around in any possible direction, and I can move around some small step such that I'm still inside. That's true. Okay.
Yes,
Now, in
yes,
addition to, now let's say instead of this, you are asking about some other situation, which is
yes. There are some directions which cannot be reached from within, means that direction which cannot be scaled down to lie within an open ball, small open ball around the point in question.
so right. So for I can maybe give a pictorial argument here, but can maybe show this for a particular example. So just like in our case, let's just take a 2D case, okay? And let's say in 2D case we are at some, let's say we are just here on the x-axis for some reason. So this is the open ball, right? If I were to, so minus the shell, but this will be the open ball, right? Is that correct?
Yeah,
Let me
sure.
maybe draw it properly without the shell. So what I meant was, so this is my open ball, right?
Yeah,
Now here I assume that I'm still looking in the R2 space. I said that ball with respect to this R2 space, right? But let's say I now put a constraint that I allow you to move only on this x-axis in this ball.
okay, okay.
So in that case, what do you think will be the will be the play directions in which you can
Yeah,
move?
that will be that will be an interval, right?
Yeah.
Open interval.
But now, if I say that, uh, you took the ball, but you took the ball open ball by mistake in R2, but actually you're allowed to move only in this x axis because of some constraint in your problem.
Yeah,
So now it's a problem, right? Because we defined openness with respect to some other space. Actually, we wanted to define openness with respect to a certain different space. So what you have asked is about openness.
and reachability kind of, quote unquote.
Openness is relative to a space. It's not an absolute concept. So openness, whenever we say with respect to a certain set, relative to the set. I mean, I'll just say set y, but what I really mean to say, so here y is actually r1, or maybe let me not write y, let me just write s to not confuse you. S is r, or yeah, s is r. You are allowed to move only in this, okay? R union, or maybe to avoid any confusion, I will write x0, x belongs to r. So I hope this is fine. But this blue ball is actually I'll just write the standard notation. So this is the ball centered around some point x0 with a radius some r. This is a subset of R2, right? So
Yeah,
had I defined with respect to the open set, the open ball at this point x with respect to the space, so what I want to write, I think I'll end up overloading the notation, but please bear with me. So what I'm trying to say is, here actually I will write R2. So the ball superscript R2, okay? This is this ball, the blue ball. Now let me erase that and let me rewrite something similar just to contrast with the notation that I have been using. What I am saying is, because the openness is a relative notion relative to this set, which is the x-axis, so relative to what notation should I use? I'll just write informally x-axis for now. X-axis x0 R. And the point that I am saying can be written as saying this. Does that make sense now? I hope that answers your question.
Yeah, means the ambient space we have to define with
Yes.
respect to which you are
Yes.
defining openness,
Yes.
right?
Because the metric depend, like metric will be rather restricted to this, the set that you're looking for, or maybe it's already restricted to that set. So depending on that, the points contained in the ball will change.
Okay. Yeah.
All right. Any questions? Any other questions before we just jump into the questions? I hope at least the idea is clear for what are these first order and second order necessary conditions. So if there are no questions, then I can start with the week 2 questions. Okay, alright, let's start. So, alright, we question 1 says that for an optimization problem, the global minimum is unique. Is this true or false? And what's the proof in either case? Any thoughts? Dhyanesh, Muteya, Navendu, any thoughts? Okay, so I'll just if you want I can write the whole thing, but I'll just leave it at the picture because it will be self-explanatory from here only. So if I can just define y equals to, it's a straight line outside this region, let's say -2 to 2. So this is a counter example which says that obviously global minima need not be unique. How about this? I think we did cover this proof in last week's discussion, but let me still just confirm if we recall this idea. Are isolated local minima strict local minima? Is it true, false? Hello, I hope you can hear me. At least confirm that.
Can you explain this concept? I have confused in isolated local minima.
Sorry, can you speak up a bit? I am not able to hear you.
I have confusion in isolated local minima and strict local concept. Can you explain this?
You mean the definition or this statement, like what the proof for this statement?
No, concept.
Okay.
Concept wise, definition wise.
Okay. Just give me a second. Let me go back to the last week's notes. I think I have it here, the figures. If not, I'll have to go back. Just hold on. Okay, I don't seem to have the figures. It's okay, no problem. So strict local minima, at least I hope the definition is clear. I guess you're asking for the distinction between the two, right? Hello?
Yes, sir. Yes, yes.
Okay, yeah. So strict local minima simply says that the usual local minima definition, but there exists some epsilon neighborhood such that f of x is greater than f of x star in epsilon neighborhood around x star, okay, for all x in such. So that's just the strictness. So the strict local minima comes from here. It's a strict inequality. Now what isolated local minima is saying that you give me some, you give me a point. Let's say this is the point x star, which is a local minima. Now I am saying that I can provide you with some neighborhood around this point. So let me extend this function and say something like this. Okay, let's say this is what the function looks like. So what we are saying is this is an isolated local minima in the sense that I can find some neighborhood around this point such that in that neighborhood this x star is the only local minimum. Do you follow that? For example, if I were to say let me give the example similar to what has been given in the class, but I'll use a slightly different term. So if you have something like a sine 1 by x, so what's going to happen is around the 0 there are going to be infinite oscillations. Okay, so here no matter how much of a small neighborhood you pick, so in the class, by the way, he gives an example of x to the 4 cos of 1 by x. Doesn't matter, you just want a sinusoid, whether it's phase difference or not doesn't matter, but it's cos of some sinusoid of 1 by x, so that you get lot of oscillations around the point of singularity. So here that's the point x equals to 0. So around here, if you zoom in, no matter how much you zoom in, it always looks like this. This wiggly thing it keeps on happening no matter how much you zoom in. So you can never find a ball around this point, an interval around this point x equals to 0, such that there's only one local minima or one local maxima. Here, I'm pictorially, I'm just trying to ask you, pictorially, do you see that there is a neighborhood that you can put here in which only x star has the lowest possible value? I mean x star is the local minima. Hello? Sorry, is it clear, or you want to explain again?
No, only one local minima will be there, like x star only.
So here I can find you some neighborhood such that x star is the only minima there. That is what we mean by isolated local minima. Okay, strict local minima does not mean that it's isolated. Strict minima just says that again this is a strict minima and an isolated local minima. Because in this point around x star, I can find some neighborhood where x star is having strictly lower value than any other x. Similarly, I can find some neighborhood such that in that neighborhood, x star is the only local minimum. Local minimum, the usual definition, f of x greater than or equal to f of x star for all x in that neighborhood. And that's the isolated local minimum. So this is both isolated and both strict and isolated local minimum. Is that fine?
Yes, yes.
Okay. So yeah, what is the answer to the question? This particular question? We have already seen it. proof in the last discussion, but does anybody have any thoughts, any comments on what would the answer be to this question?
It should be true, right?
Yeah, it has to be true, yes.
Because if it's isolated, then there cannot be any other minimum, right? Then
I can use the same neighborhood. So by
Yeah.
definition, it's true.
So I have a question. If you go to the yellow curve that you have drawn above,
Yes.
so if I take any point on the bottom segment, the x-axis,
Yes.
so any point of them will be neither a strict nor a local minimum, right?
It will be you mean isolated, neither strict nor isolated.
Yeah, neither strict nor isolated.
Correct, yes.
That will be the case.
Correct, right, yes. Okay, so let's maybe now compute some gradients just to become a bit comfortable with this vector calculus, because you'll be needing a lot of it in the coming lectures. So what I'm saying is I have a vector valued multivariate function. So the function is the arguments are x1 and x2, and the output is also a vector x2 and x1 square minus 2x2. So the question is, what is the Jacobian of this function? Any thoughts on how to start?
So you consider all the functions as components, right?
Right.
The top row as function f1 and the bottom row as f2, and you just compute f1 with respect to x1 and x2 with respect to f2. Sorry.
So it had to be slightly careful here. Just in general, if you will have an m cross n matrix, you need to be sure which one is m and which one is n. That's a bit important, because accordingly you'll be multiplying this. You'll be using this as a linear transformation to solve a few systems of equations. So in general, what you can keep in mind is, if you have a function, what you do is what for us typically what we are used to as gradient, you just take a transpose of that, write as a row vector for each one. So this, let me call it f1, this let me call f2. Okay, again f1 of x1 x2, f2 of x1 x2. So I am skipping one or two steps here, but I am hoping that this is clear. So this, I'm just calling this component of f as f1 and this component as f2. So in this case, since you have a vector, so we do as always, this is a vector. When you want to write the Jacobian of this, the way we write it is, you take the first component, you take the derivative with x1 and x2, just write it as a row vector. So x1 and x2, by the way, are the variables with respect to which we are differentiating. So here is the 2 cross 2 case, so it's fine, but in general need to be a bit careful about this. That's why I'm writing it like this. Okay, and we do the same thing now with respect to f2. Okay, exactly the same thing. Sorry, not with respect to x2, for f2. Okay, so here the function is pretty straightforward. So what does it turn out to be? It turns out that the Jacobian here for the function f at the points x1 and x2, this is just one way to denote this Jacobian for the function f. If you just compute it, it will turn out to be 0, 1, 2x1 and minus 2. Right? So for example, del f1 by x1, there's no component of x1 here, so it's 0. With respect to x2, it's of course 1, because del x2 by del x2 is 1. This expression, if you differentiate with respect to x1, you have 2x1 and here it's minus 2x2, so you get the minus 2 term. So it's just the simple partial derivatives. So these are, I agree, somewhat straightforward questions, but like I was saying, it often we make mistakes. At least that's what I've seen in writing the Jacobian. So it's a good exercise to just go through it once. Another straightforward question. You have x cube minus 6x square plus 12x minus 5. What are the stationary points of this function? So what does it mean to say stationary points? That's the first question. What are stationary points? How will one find it?
Derivative should be 0.
Yeah. That's the definition of stationary point. Now, depending on the second order conditions, whatever we find, we can say whether it's a local minimum, local maximum. But this just tells us it's a stationary point. Okay, this does not, it's just a necessary condition. Doesn't tell us anything about whether it's a minimum or maximum. So if you solve this, again, because simple algebra, I'll just be slightly fast. So this simply means that x equals to 2. That's the only stationary point they have. This function has. So along similar lines, if I say that I have a quadratic function, and let's say the minimum is at x star equals to 2. So what is the value of p? So here again the same, we're just going to use the same information. So we take the equal derivative to p 0, and this will give us p equals to minus 4. Okay, but here note that I was given a much stronger condition. I am already given that the minima is at this location, and I have to comment a bit about the behavior of the function. Meaning, for example, here find the coefficient b. So this condition was pretty helpful here. But if I just look at situations like this, and at the most I can say there is some stationary point, but beyond that I cannot say something more. I'll have to go to higher order derivatives to say more about these points and the behavior of the function at these points. How about this? If function is this sin x by x, and what we have to do is we have to minimize this function over the minus 2 to 2 interval, close interval. So how can you find this? Any thoughts? No thoughts? Is it? I mean, can we even solve this? That's the question I have. Can we even solve this? That should
So
be the
it's
first
not
question.
differentiable at the origin, right?
More than differentiable, can you say something more primitive? Differentiable is assuming something already. So what I'm trying to ask is,
Maybe
yeah, yeah,
it's not probably defined at all the points, especially at origin, right?
yeah, precisely. So the problem is, first of all, f is not defined at x equals to 0. So it is discontinuous at 0. So here typically I would apply Weierstrass theorem, right? Because seems like a continuous function, so seems like a continuous function, although it isn't, and it's a compact interval. So if I were to find this, I would say that yeah, I by Weierstrass theorem I can say that it's a compact interval, it's a hopefully a continuous function, and hence minima exists, and I can find that. I can't. Okay, I can't. So this is another instance which illustrates the okay, which maybe in a way tells you that Weierstrass is giving you some characteristics of a function, like I was saying in the last discussion, to guarantee that okay, there is a solution for this optimization problem. Okay, so here you cannot use Weierstrass. So we can't use Weierstrass to claim existence of the optimal solution. As f is discontinuous at 0.
But one thing we can do, we can check the limiting value, right, at x tends to 0. That we can do.
Yeah, but a function is not defined at x equals 0, right? If you can maybe
Yeah.
define it separately, but you have to define it, right? If you put that in the definition, yeah, maybe you just put that value at 0, and remaining you just keep it as it is. Is that fine?
But as it stands, we cannot solve it, right?
Yeah, as it stands, we can't solve it. Let's try a few more questions. We have about an hour left. X cube plus 3x square minus 7x plus 12. We have a cubic function, and there is a similar question here, which is x belongs to the intersection of these open intervals 0 to 6 and 5 to 10, and I have to minimize f of x. What about this? Can I say something? Can I say something here for this problem?
So we can club two intervals together, right? Because they have an overlapping part, right? First of all.
Yeah, so we can just write it as 5, 6, but it's an open interval. So now what can we do? Apart from plotting and explicitly checking. So maybe let me just do this one step and see what happens. And what does at least let's check the discriminants. Okay, this discriminant will be fine, I guess. Let me still minus 6 plus minus 26 plus 84 by 6. So how much will this be? 84, 91, 20 plus 6 plus 84, So this is like roughly 11. So what will the solution look like? 5 by 6 or minus 17 by 6, like roughly 3, minus 3. So first of all, critical points are not lying in this. That's okay. I mean, let's say even if they were, can you say something about this problem?
So maybe we can find if the equation is objective is increasing or decreasing at the very least, right?
Okay, so that's the derivative that we found, right? Derivative itself is a
Yeah,
quadratic
means
function. What was it? 3x square plus 6x minus 7. So this will be at
so
least
is the-
2575
yeah.
plus 6 5 30 23 and less than 336 3 is 108 36 minus 7, so this is 29 137. So it's less than somewhere between these values, and
Yeah,
it's
so it should
and
be
it's a quadratic
positive, right?
function. Sorry.
It's positive, right? So it should be an increasing function, the objective.
Okay, yeah, fine, that's okay. So you notice that in this case it's positive for all x in, sorry, open interval 5 to 6. Now
Now we can check the values at the extreme points, means at the
but
left
5 and 6 are not
boundary and the
included,
right.
right?
Yeah, that means the limiting values, I mean to say.
No,
As
but the
taken
thing
from the
is,
left
I have
hand.
to find the minimum, not the infimum. Strictly monotone. If function is strictly monotone, so let's say you have something like this, but if I don't allow you to include the endpoints of the interval, what does it say? Does the minimum exist?
No, then it's not attained, right?
Yeah,
Not attained.
exactly. So here also I can't invoke Weierstrass theorem.
Okay, means minimum, when you are asking for the minimum, we are implicitly assuming that it should lie in the feasible region, right? It's,
Yes,
otherwise
yeah.
it's-
If we write infimum, it's okay, but we are writing minimum because we are always
Yeah.
interested in attaining the point, right? If we just write infimum, it's of no good to us. Good to us. In a limiting case, something may happen, but of what use is that?
Yeah, got it.
There is a function quadratic in both x and y. Now the statement is the stationary point of this is a global minimum. So whatever stationary point this function has, the claim is that it's a global minimum. Is it true, false? So what is the information that we are given? It's a stationary point, right? So let's try using that. So what will it give us? X and minus y are 0, right? So this implies xy is 0. I'm just equating the partial derivative. I just skipped a step here, but just wrote the partial derivatives with respect to x and y. X and minus y are those derivatives, and I just equated them to 0 because that's the stationary point definition. So is this a global minimum?
false, right?
Yeah, why is that?
Because you can take any value like x is equal to 0 and y some finite value
Yeah,
to be negative, right?
yeah, precisely. Yeah, it's not bounded from below.
Yeah, it's not wrong.
Now this is again just an application of definition. So here we need to check. What we need to do is we need to look at x transpose ax. So let's just take a look at that. And this is again just to make sure that we are clear with the definition. So let's just quickly take a look at this. You have x1, x2, 16, 14, 10, 9, x1, x2. Okay. So what will this amount to? x1, x2, 16x1 plus 14x2, 10x1 plus 9x2, and if we again do this inner product, what we'll ultimately end up getting is 16x1 square plus 24x1 x2 plus 9x2 squared is nothing but 4x1 squared plus 4x1 plus 3x2 whole squared, which is strictly greater than not strictly greater than 0, because I assume that x1 and x2 are not equal to 0, otherwise it's trivially true. So what we are trying to recall here is, if we have x transpose ax, so actually maybe I'll introduce a different symbol which you will see in a lot of books. You will see a notation like this. If you are not familiar, this might seem a bit strange. So if I put this curvy inequality with a dash at the bottom, it means greater than equal to, but this is an inequality for the matrix per se. So this part x transpose ax, this curvy inequality greater than equal to 0, that's called positive semi-definiteness. Can define similar thing for negative semi-definiteness. And if I remove these equality signs, these are called strict inequalities, so then it's a positive definite or positive semi-definite. In our case, one more way to check it would be just to do this, take the determinant. So this is clearly 4 and this is greater than 0. The determinant of this matrix is non-zero, which shows us that the eigenvalues, none of them are zeros, which is another way of saying that the matrix is positive definite. So I hope that you are familiar with this fact. It will come in handy in the
So the curvy arrow which you wrote is a general.
We write this for matrices. So if you want to say PD, positive definite, negative definite, then you can use this.
Okay.
So okay, I think I'm extremely sorry. So here it's just a regular arrow. I'm sorry, made a mistake here. So here it's a scalar, so it's just a regular number. What I meant to write was the following. If you just use the matrix, then you use the curvy arrow. Okay, yeah, sorry about that. So whenever
that's what I was wondering.
Yeah, sorry.
Yeah.
Okay. One more question, which is, okay, yeah, let's see. This is sine x plus cos 2x of x is 5x squared. F of x is sine x by x. There's one more function, 3x squared minus 12x plus 12. So let me name them f1, f2, f3, f4. Which of these fi's have local minima equals to global minima? Like which of these functions are such that are the ones which have local minima which happen to be a global minima? Is the question clear?
Yeah, I think this should be for only functions 4 and 2, right?
Why do you say that?
Yeah, f2 is a convex function like a parabola, so
Right. Same for
and that
F4.
same goes for f4.
But
Same
what
goes
about
for
F1?
f4, yeah.
F3 we saw just now.
Yeah,
So,
f3.
but what about F1?
F1 I believe is a periodic function, so mm, can we define something as a I'm not sure.
Okay, so,
Yeah, I think f4 yeah, f1 also I think it's possible.
okay, so just be slightly careful. So just plot it out once. So here you have a factor x and 2x. Okay. So what you'll end up getting is you'll get some minima of one scale and some other minima of other scale. So that's why not all the local minima will be global minima. Okay, just plot it once and check it out. Okay, just two more questions from this week, and then we'll move on to the week 3. And let me know if you have any questions in the class material as well. So here again we have a function involving two variables. I was about to say quadratic, but I just now realize it's a y cube term here, not y square term. So it's not a quadratic, it's a cubic function. And we are looking at a particular set where the gradient happens to be 0. So question is, what is the size of C? How many elements are there in this set C? So this is just computational, so let's just do it. So the gradient that we have with respect to x and y separately, what we can do is we can do it, we can write it as x plus y minus 4 and I think x plus 4y minus 3y square. And if we equate it to 0, will imply so again I'm skipping steps here, but you will get two solutions, 4 0 and 3 1. So you'll get two solutions, so this implies cardinality of C is 2. Okay, it's just a straightforward computation, and again this is just as far as I understand, first thing that is obvious is why would we be interested in these kinds of sets? Well, because these are the stationary points, so you'd want to pick one of these, and ideally it would be great if you could just pick each of these and check. So for example, here there are only two candidates, so we'll just check which one has the lower value, and of course you still cannot definitively conclude because it's a necessary condition, but this definitely reduces your search space to these two elements. Okay, but in general you may not get this. In general, this C set may be pretty big. So there is a similar question, not a similar question, but just some computations. So we have a function defined which is as follows: xy times e to the x square plus z square minus 5, and the gradient of f at 1 3 minus 2 is given to be some alpha 1 n minus 12. So if we write down the gradient expression and if we equate it to alpha 1 minus 12, so point is what is alpha, and if you just do this algebra you will get alpha to be 9. So I am not doing this because just calculation, there's really no concept involved here. If you are finding it difficult, just let me know next time, or maybe now if you have any questions. Otherwise we can move on to the assignment 3 questions. Any questions about week 2? So thus we'll move on to week 3. So there's only one, at least given the time we have, we'll just focus on one very crucial aspect which we will see more about in the coming weeks. So we'll quickly go through that and then go through the week 3 questions and conclude the session. If you have no questions about week 2, please let me know so that I can move on to week 3. Yes, no, some comments, some answers, something, anything. Okay, I will take that as a no, so we can move on to week 3. Okay, so this precisely this one thing which it's a nice explanation that the instructor gives in the lecture, so I just want to make sure that we are on the same page regarding this. And the topic of discussion is as follows. So by the way, I hope that everyone has seen week 3 lectures. Is that correct?
Yes.
Okay, fine. So there is a theorem that the instructor says. There is a theorem that the instructor talks about, which is saying that if I want to solve a problem of the following kind, maximum such that f(i)x is alpha for all I in M. So if you're not familiar with this notation, maybe let me just write in the simple way. I is 1 to M. And for simplicity, we'll assume that these functions are continuously differentiable. So it's just a notation, shorthand for this. The functions fi's are differentiable and they are continuous. The derivatives are continuous at x star. This is the local maxima. So then what and of course these fi's is very important, but this is precisely where my question is. These are assumed to be linearly independent. Why do I need to assume this? So okay, maybe let me complete the statement. So let's just keep it as it is. Let's just take this at face value, linear independence. So what this theorem says that maximize this function such that such and such constraints are there, and suppose these constraints are such that the gradients are independent. So excuse me, my bad. I didn't mean to write the fi's are linearly independent. I meant to say that the gradients are linearly independent. So grad fi are linearly independent. Okay. So then the theorem says that there exists some vector lambda star such that gradient f0 x star is basically a linear combination of gradients of all the individual constraints. So the question that I have is, why do we need this linear sorry, why do we need this linear independence condition? Because this will ensure that you have understood why we are defining things the way they are. These are what are called constraint qualifications. This is one way of defining constraints, but and I think we'll probably be covering that towards the end of the course. Maybe, I'm not sure. But have you people thought about why we want to define these FIs with this strange looking constraint? Like, why would I want the gradient FIs to be linearly independent? Where am I using this linear independence?
So we are writing the gradient at that optimal point as a linear combination of the gradients, right?
Yeah, correct. Yes.
So we want those to span the tangent space, right?
Sorry, come again.
No, I'm telling you want the vectors to be independent so they span the entire tangent space, right?
Tangent space of what?
Means the instructor was saying, like, we want the tangent space at which we want the derivative to lie in. I'm not absolutely sure about that, but is it something related to that? Means
Yeah, it's related to that, but what you said, it needs to be corrected. So yeah, you are right that it's about this 5-10 minute discussion in the video. But yeah, the point is, what is he trying to say there? It's definitely related to that. Because this piece is very crucial. It's not just we come up with random definitions for no reason and just apply them. Especially when you're seeing that there's this really important proposition, and if you want to ensure that we have understood it correctly, we need to make sure that we understand why we are imposing these conditions for the theorems to hold true. So think out loud. This is a discussion session, so don't worry about whether you get it wrong or whether you don't get it on the first try. It's not relevant. Let's just think about it. So what Soumyadeep said, let me just write these points down. So he's on the right track. So what he's saying is something about the tangent planes. But the point is of what? And of course,
right?
Sorry?
And tangent planes that are defined by the constraints, right?
Tangent planes
means all the gradients will define are normal, and those normal defines a plane, and we want an intersection of those planes, right? At the optimal point.
Not quite. So you are talking about the same topic, but not quite. So let me give another hint. So just about what you said. If you have let me just draw a contour plot. So like you were saying, you talked about surfaces, which means that I'm assuming you're talking about these inequalities, right? Sorry, not inequalities, these equality constraints. So before that, let's just take a simplistic setting where you look at f0, the objective function, you look at the level curves for this function f0. So what you are saying amounts to pictorially being something like this, right? The gradient f0 at this point, let's say x0, that will be gradient f0 x0, right? That's what you're saying. This is normal.
Yes, okay. The normal.
Yeah, so then we'll just assume that if you go inside along this concentric paths, then C increases. So just like how it's done in the convention that's followed in the lectures, just for the sake of illustration. Yeah, so okay, so now you have these gradients fi, f0s, and similarly you have the normals pointing for each of the constraints fi of x's. So what were you saying about these gradients now?
Uh, means I uh, means which point means I'm also getting confused.
Okay, so
Means I am telling that
yeah.
e- each of these gradients will define a direction, and that will, and which will define one tangent plane, or here a normal line. Means tangent line in this case, in this 2D case.
So the question is how it's defined. You are on the right track. So just again to elaborate on this example, let's say that when we go inside, let's say the C increases. Okay, so basically we should go along this direction. No matter where we are, we should always point towards inside to be in the hopes that the function value increases. That part is fine. And what you are saying about the gradient directions, that's going to be useful to us somehow. Now, one question I have as an intermediate step towards the answer that we want, and it is, let's say if I move along this surface, okay, maybe let me use a pointer. Let's just move along this surface. Does the function value increase or decrease?
No, it remains same,
It
right?
remains the same, precisely. Yeah, it doesn't change at all. It doesn't increase, doesn't decrease. It doesn't change at all. So, the same idea when you are to apply to, let me come back to this. So, let's say you have to satisfy the constraints. What does that amount to? So, let's say instead of these, and let's say each of these is a constraint. Let's say this is F1, F2, F3, F4. So if I want to satisfy all these, so here anyway, I mean, you can say, okay, they don't intersect, so there's null set, no feasible point. But just forget about that for now. I'm just talking about the fact that if I want to make sure that I satisfy these constraints, what can I say about the gradients? Like how can I move? If I'm moving, what is the relation of the directions in which I can move with respect to these gradients? Let's say gradient f0, gradient f1, gradient f2, gradient f3.
So I
gradient
should
f4.
move perpendicular to the gradients, right?
And why is that?
Because in this direction, the gradient doesn't have a component, so it doesn't change the function.
No. So okay. So you are alluding to something that we will be alluding to. But before that, there's an intermediate step which we need to finish. We can't skip that step. We have to satisfy this constraint, right?
Yeah.
So if we have to move along
yeah.
these paths, then we cannot escape one fact, which is I can only move along these directions. Okay. Is this part fine?
Okay, so we want all directions that are orthogonal to the gradients, right?
So we don't want what we want is we want this fi of x is alpha. I mean alpha I, whatever it is, whatever the constant is, alpha I think. Yeah. Some constant. So this constraint is telling us that when I'm moving on these level sets, on these surfaces, that forces me to do this, right?
Yeah. That I got. That I understood.
So what I'm saying is there's a difference between saying I am imposing this condition versus saying, I this is exactly what I wanted, and as a consequence I am getting this. Are you with me?
Yeah, means I am a little bit lost about the last question.
So what I'm trying to say
you
is,
said.
if I have fi of x is alpha I, this feasibility constraint, this will imply this condition absolutely. If I'm
that is true.
if I'm
Perfectly
just
fine.
given this,
Yeah.
then it means that there are at least this many constraints. Maybe there are other constraints also. I cannot say anything about that.
Yes, true.
Okay, you will see something later on called active inactive constraints. So I'm just trying to say that it is with this condition in mind we reached at this conclusion that we would want to move along such directions only. So this is what you are calling the tangent plane.
Yeah, this is a tangent plane, correct. That
Okay.
satisfies the
So
constraint,
this
the
is one
directions.
thing that I want. The other thing is, uh, it would make sense for me to be at a point at which the gradient is a linear combination of these. So let me use a pointer again. So it would make sense, given that this is the type of
Yes,
directions in
yes.
which I can move, it would make sense if I have a gradient for my function f0, if I have a direction which is some combination of this. Meaning that if the only way I can move to increase my function value is somehow orthogonal to the direction, the set of directions in which I'm allowed to move, then only I can say it's a maximum, local maximum, right? Otherwise I can just move around in those some component in that direction and I can increase my function value. Does that make sense, or did I confuse you people?
Yeah,
more?
it's perfectly fine. It's fine.
Okay, so this is why it, one way, again, like I'm saying, this is not the only way, this is one way as far as I understand. I think there are other ways also to impose what are called constraint qualifications, but this is the most commonly used one, at least in my as per my understanding. So this is why we would want gradient of f0, sorry, gradient of f0 to be some linear combination of the gradient fi's. So is this point clear? This is very important. Any doubts? Why now? Is it? I hope it's clear why we are defining things the way they are. So just to be a bit precise here, tangent plane to the feasible region at x star, so at some x, and specifically here, since we are imposing this equal to 0, we would want it to be x star. So in general, this can be there will be a slightly different condition, but at this optimal point we have precisely this condition. Just to mathematically say, give you one necessary condition for determining whether or not I am at a local maximum. It's just whatever we are saying verbally, that I cannot find any other direction in which I can move to be able to increase my function value in the feasible region. This is one way to make that condition, realize that condition mathematically. Okay. So let's move on to the questions. Let's see how much we can. I think we have about 20-25 minutes. Should be doable. And I realize I haven't gone through, I haven't done a recap of the things done in the class, but I still wanted to cover this this really crucial topic of why we are having these so-called constraint qualifications coming up as required conditions in these first order and second order necessary conditions. Okay, so let's move on to the questions. So the first question is, f of xyz is x plus z such that square plus y square plus z square equals to 1. Okay, and let's say lambda is the Lagrange multiplier. So what can you say about the, let's say there's an x star which is a local optimal point. So can we express this x star in terms of this lambda? How will we do that? So okay, even before you begin, is lambda vector here, scalar here, or what is it, matrix?
Lambda is a scalar here.
Yeah, and that is because,
Only single constant is there.
yeah, so depending on the number of constraints, we have uh, one lambda for each of these. Okay, so what we'll do is we will just write the Lagrangian. So if you recall from the lectures, all that we do is write the function. This is our function f of x y z, and what we do is we take that, add it with the Lagrangian multiplier times the constraint. This is our constraint. So we'll just write x square plus y square plus z square minus 1. So this is, like I was saying, it is our Lagrangian, which is a function of x, y, z and lambda. And what we do is we equate this Lagrangian, just take the gradient. We just equate this gradient of the Lagrangian to be 0. So what we end up getting is 1 plus 2 lambda x is 0, 1 plus 2 lambda z is 0, and I think 2 lambda y is 0. So which ends up giving us, maybe let me write it upstairs. So these are, by the way, x star. At x star lambda star. So we are going to get actually, yeah, doesn't matter, whichever lambdas can change the sign. So x is, I think in the assignment given the options, I mean, don't mind the sign, you can just multiply everything by a minus sign to get the answer that we are getting. So what we are getting is minus 1 by 2 lambda 0 and minus 1 by 2 lambda. Depending on how you write the constraint, you will have that extra minus sign coming as a multiplicative factor. So this is just to get you used to applying the definition of Lagrangian multipliers. Now here, if I wanted to find this lambda, how would I find lambda? Because lambda is not known to me. Lambda itself is a variable. So how will I find lambda now? So it's like I defined x star, my answer, in terms of some unknown. But how do I find that unknown now? So it's the same question, but how do I find lambda star? Because I want to, ultimately I want to find x star. But x star I have defined one unknown, I have defined in terms of another unknown. So what do I do now? I think there seems to be some connection drop. Can you hear me, Navendu?
Yes.
Okay. All right. So keep in mind that we always have to satisfy our constraint. So although we have expressed our unknown x star in terms of another unknown lambda star, we still have this one more equation to help us. So we have two unknowns, x star, lambda star. This was one set of equations, and you have another equation. Okay. I mean, you have one equation here, and another equation here, and you have two unknowns. So you can find both the unknowns. So we'll just do precisely that. So we'll just put x star here, x star, y star, z star. What I meant was x star, y star, z star is this. So I just put that in the constraint. x star square plus y star square plus z star square this is 1, and that basically gives me lambda star as plus minus 1 by root. Okay, let's look at a few more questions. So one question is maximizing over xy f of xy. F of xy is given to be specifically 2y plus x, and the constraint is y square plus xy minus 1 equals to 0. So here we have to find critical points. And as we have been doing all along, so what we'll do for that is we will define Lagrangian to be this function minus lambda times the constraint, I mean just plus 1 minus xy minus y square. I just change the sign, doesn't matter much. We will equate the gradient to be 0. And what we will end up getting is 1 minus lambda y, and you will have 2 minus lambda x minus 2y. You have to equate this to 0, so this implies basically what we'll end up getting is okay, y square plus xy is 1, and right, so this thing would mean that y is obviously not 0. If it was 0, then this 1 equals to 0, which doesn't make sense. So what we can get here is lambda star is 1 by y star, and minus x by y is 0, which implies x is 0, which implies y square equals to 1, which implies y is plus minus 1. So we just all that we have done is just made a simple observation from this constraint that y first of all can't be 0, and once we use that here, all that we can say is lambda is 1 by y. So I think I might have made a mistake here. There is a 2 lambda. I think this is what I was missing. So 2 lambda y. So this 2 minus 2 is 0, and x by y is 0, and so ultimately our points of interest are 0 plus minus 1. So this is just to get you familiar with how do we use this Lagrangian. So think to partly illustrate this point that, as the instructor was saying in the lecture, you have, let's say, m constraints and you have n variables to optimize. So you will accordingly have m plus n equations. So you'll have to use all the equations to find all the unknowns, because in addition to the variables for which we want to find the values, we are also introducing these additional unknowns, which are the Lagrange multipliers, the lambda stars. So to find those we'll have to often deduce some relations about the variables of interest. For example, here we looked at the constraint and we could see that okay, y is definitely not 0, and we could then use that to, along with the first order condition, determine that okay, lambda and y are reciprocal of each other, and then substitute in the rest of the equations to then ultimately find the candidates, the stationary points of interest. So continuing to with the same question, this question that we have. So we have maximize, same question, maximize 2x plus y such that this is the constraint. Now is the point 0, minus 1. That's one of the candidates. So is 0 minus 1 a local maximum? So what I'm trying to say is we are given x star, y star is 0 minus 1, and from our relation that we just computed, lambda star is 1 by y star, so it is also minus 1. So what can we say about this? This is a local maximum. I mean, I want to check whether it's a local maximum or not. So how do I go about that? Any thoughts? Okay, so remember that the first thing we need to check for these questions, you are given, let's suppose that this is a local maximum, and we want to see if the theorem requirements are met or not to be able to make a conclusion. Note that we need to be able to satisfy the first order conditions. So what are the first order conditions? One of the things that you would need to apply this Lagrangian multiplier machinery is that the derivatives of the constraints are linearly independent. Here, since we have only one constraint, what we need to do is we need to look at the gradient of, what's the constraint? Constraint is xy plus y square minus 1. This is my constraint. The constraint, take the gradient of this, which will turn out to be y and 2y minus 1 at this point, will be minus 1 and minus 2. This is not 0. Okay, so gradient, so the constraint qualification that we have said, that the gradients of the constraint should be linearly independent. So the grad of constraint not 0 is satisfied. Great. So one thing is at least going fine. Let's go and check the rest of the things. What does this say about the directions in which we can move? So remember, I was talking about this set of which is the tangent plane to the visible region. These are the set of directions in which we can move, and we already saw very trivial exercise questions where we were computing such directions. So let's do that for this case also. just to get an idea of okay, how much room we have to move around, so that we can check along these directions whether indeed this point is a maximum, local maximum or not. We'll just go by first principles. So you have C x star, y star, lambda star as the set of directions in which we can move. So they'll simply be D such that they're orthogonal to this gradient direction. So what will this set be? So just please check this. It will turn out to be this subspace, just any multiple of this vector minus 2 1, and alpha is any scalar. So the reason why we are doing this will become apparent in this step now. When we compute the Hessian, so we compute the Hessian of the Lagrangian. So till now what we have done is we have checked for the first order conditions. Let's move on to the second order condition, because first order conditions gave us a few things. They gave us the gradient direction orthogonal to which we should be moving. They gave us candidate points for to determining which is a local maxima or not. They gave us the value for the Lagrangian multipliers and so on. So we'll now try to use the second order information and see what we can get. Okay, so if we compute the Hessian, meaning just like we are computing the Jacobian, when we compute take the derivative of this vector, what we'll end up getting is the following. So if you are not clear about the steps, just let me know. So I'm just skipping that one small step of calculation. I'm just directly writing the Hessian. Right, so you had the gradient vector to be 1 minus lambda y, 2 minus lambda x minus 2 lambda y. So I've just taken the partial derivatives with respect to x and y for these terms. So for example, here you get a 0 because there's no x term. You get a minus lambda here because the derivative with respect to y. Similarly, you get a minus lambda and a minus 2 lambda at the bottom because we are differentiating with respect to x and y respectively. So okay, what we need to do, by the way, is put lambda star equals to minus 1. That's what we found at this point of interest, at this stationary point of interest. So this will basically give us 0, minus 1, minus 1, minus 2. Oh, sorry, there's a minus lambda, so all should be plus. Now notice that here the determinant is strictly negative, and we may be tempted to think that okay, it's just negative definite, and hence this is a local maximum. But please keep in mind that what we check, so we let me just write this, we are not checking whether W might be confusing. X transpose, no, okay, W is a better choice, sorry. Yeah, W transpose, let's call this Q, capital Q. So W transpose Q, W less than 0 for all W. No, we are not doing this. Okay, what we are checking, whether W transpose QW is less than 0 for all the vectors, for all the directions that are feasible, the feasible directions, which we just now saw, x star y, c of x star y star lambda star. So what I mean is this set. Okay, so all we want to look for is this particular set of direction, because this is where we are allowed to move at this point, these directions, along these directions. Okay, so what we want is, if you have any vector of this form, you take the inner product of this, you take a norm of this vector with itself, but with this as an additional weight. Okay, which is what this means, W transpose QW. Then it turns out to be minus 2 alpha square, which is clearly 0, less than 0 always for any alpha. So what we have ended up doing is, the Lagrangian is negative definite. Okay, so we have satisfied a sufficient condition, and hence the answer is affirmative, that indeed 0 comma minus 1 is a local maxima. Okay, I think we will stop here. Firstly, yeah, because we are slightly out of time, and secondly, we did not discuss anything about least squares. We didn't have any kind of recap or any discussion on that before we could move on to the questions. So we will do that next week, in addition to the usual week 4 lectures and week 4 assignment questions. So I can stop the recording if there are no questions. Otherwise, yeah, I'm here for a few more minutes. Okay, alright, so let me then stop the recording.